before I start, I'd like to thank the organizers and thank all of you for staying around. It's been an excellent conference. Thank you. So today I'm going to talk about a new approach to probabilistic programming inference. This is joint work with a postdoc of mine, Jan Willem van de Mint, and Vikash Manzinga, who is here sitting next to the back. And if you're like me and extremely tired, and in particular tired of listening to talks, you can actually play around with the stuff that I'm going to talk about today by going to this website and checking out exactly what it is I'm going to be talking about, this Anglican probabilistic programming system, which illustrates a particular style of inference that we'll introduce now. Okay, before I get into the details, let me tell you what I think probabilistic programming is. Okay, so classically, at least in computer science, you are given a program, you develop a program. That program has some parameters which you also set, and then you run that program to produce output. Okay, so the outputs are unknown, the program and the parameters are provided to you, you run the program, it produces an output. Statistics is pretty different, right? In statistics, we write some sort of generative model. Okay, so we have the generative model, then we get some sort of data, X, and what we want to do is invert that generative model somehow and figure out some characterization of the distribution of the parameters that could have given rise to the observed data. I think of probabilistic programming as sort of the natural computer science analog to what we do in statistics, which is to say that what we're given is kind of the same as in statistics, but what we want to do is something like what we do in computer science. So what we're given is a program with some parameters maybe not specified exactly, and we're given the output of the program, and what we'd like to do is figure out execution paths of the program, or we'd like to figure out some sort of estimate of the distribution of the parameters that could have given rise to the observations having executed the program with those parameters. I think the goals of probabilistic programming, the research goals that I have anyway, are to like probabilistic programming should allow us to accelerate inference over models. So for me, code is easier to read and write and certainly modify than math, so you don't have to rewrite. You know, it's like black box inference. You don't need to rewrite your inference algorithm every single time you make a minor mathematical change to the model. And of course, probabilistic programming might be able to lower the barrier of entry to the development of new models. So I would argue that there are more people that can code than can do math well. We'd like to be able to accelerate iteration over inference procedures as well. So if you think about probabilistic programming languages as an abstraction layer, as an abstraction boundary, then you basically have a model library that you can test inference algorithms against. So if you're working on inference, then you might like to be able to actually see how your inference algorithm does in a very, very wide variety of models. This is what I mean by accelerating iteration over inference procedures. And of course, we'd like to be able to think about, and this is maybe the biggest reason to be interested in probabilistic programming, is the development of new, richer, more expressive models. So probabilistic programming programs are richly expressive. So today, I'll try to situate Anglican and the work in this talk relative to related work, and I'll do a little technical introduction because I don't think I can assume that all of you are familiar with probabilistic programming. And I'll talk about the contribution, which simply stated is basically realizing that particle Markov chain Monte Carlo techniques can be applied to probabilistic programming inference, and that doing so results in some gains in efficiency. I'll talk about Anglican. This is the probabilistic programming system that we developed, a research probabilistic programming system that we developed to test some of these ideas and prove them out, and then show you a couple of results. You may be familiar with some of the application-driven probabilistic programming languages like Bugs and Stan and Jags. We've heard about some other languages even here at this conference, notably the use of blog. Anglican is more comfortably situated in and amongst the Turing-complete, richly expressive languages, basically introduced in the Church paper not that long ago. So Church was a language developed largely for expressivity. Inference was not that great in it. The the sort of current state of the art prior to this paper was a single site Metropolis Hastings algorithm that I call random database, but the paper title is something like efficient inference via transformational compilation or something like that. So Anglican is in the same expressivity class as a Turing complete language, but uses a completely different inference technique, namely particle MCMC, which is more efficient, and leads to a research path towards probabilistic programming scalability that we've started to explore. In fact, there'll be a paper appearing at this NIPS called Probabilistic C that takes some of the ideas and pushes forward. Venture is in the same expressivity class, and this is Vikash's probabilistic programming system, but includes, it has a broader scope and includes things like inference programming that these languages do not. Okay, so probabilistic programming preliminaries. So in a probabilistic program, procedure is a sample. When you execute a procedure, you run a procedure, it generates a sample. This means that programs themselves are generative models. So when you write a program, it's just a generative model. Inference is basically the same as trying to figure out what execution paths in the program or execution traces of the program could have or were likely to have given rise to the observed data. And of course, different traces arise from encountering and applying random procedures, either elementary or compound, encountered in an execution path of a program. So if you're executing the program and you hit a normal procedure, then that program will evaluate in a particular execution path to a number at that point. We'll see. We'll be a little bit more detailed about that in just a second. And of course, observations, data, the observed values that you want to condition the execution of the program, show up as weights essentially on these execution traces. So since I'm talking about probabilistic programming, and I've said that your generative model is a program, it makes sense to give you some sort of syntax to think about. So today I'll be talking about a modeling language which we borrowed from Venture, which has Venture-like syntax and semantics. And there are basically 3 outer directives and then a bunch of inner expressions. So the outer directives are assumes, which are variable declarations, observe, which is, you can't see the red dot at all. Observes, which are statements that allow you to inject data or observations into your program, and predicts essentially are printouts of expressions evaluated in the printouts of the random variables of functions of the random variables in your program, or the functions of the variables in your program. So all of the inner expressions are scheme or Lisp expressions, i.e. plus 8, 9 evaluates to 17, of course. Functions are first-class objects, so if you see something like lambda AB that says that that expression evaluates to a procedure that has the particular, that does the thing in the next parentheses. And of course, you could apply functions to lists of arguments and evaluate expressions and all the standard stuff that you can do in a programming language. In order to talk about improved inference in probabilistic programming systems, I need to establish a correspondence between generative programs, i.e. the programs written in this syntax, and execution trace probabilities. Okay? So this is an example generative program. We won't stress too much about this because I'm going to go through this in great detail. But basically, there are a couple of POIs, parameters of interest. Okay? And the generative model has 2 parts. There are 2 functions that make up the generative model. There are a couple of observations, and we want to predict the values that those parameters of interest take given the observed data that we have here in 18 and 6. Okay? Okay, so we've got the language. Now let's do a little bit of math. Okay, so what's how do we define the probability of an execution trace? Okay? So eventually what we want is we want the conditional distribution of all of the random variables generated in the course of a program execution conditioned on the observed data. So the observed data is going to be the set of y's, and the set of random variables is going to be, this is very compact notation, but the set of random variables is going to be x1 to n. Okay, so what we want is we want to be able to sample from this conditional distribution of the random variables inside the program, the random variables generated in executing the program, conditioned on the observed data. Okay, so we're going to say that that's just proportional to a joint, and we're going to define the joint to be a product of a bunch of things. So we're going to take a product over in observed statements. So however many observations you have, we're going to have this number of observes, and the observed expressions are going to be denoted by G. Yn is going to be observed data. Theta is going to be a parameter of the observation distribution. The type of the observation is Tn. Both of those things can be arbitrary functions of the interpreter memory state up until that point. And then F is going to be the mechanism by which the interpreter memory state evolves. That, of course, is interpretation of the underlying code, i.e. generation from the generative model. Okay? So forward execution generates sequences of stochastic procedure applications, i.e. draws from these F distributions. So to get to an interpreter memory state xn from x1 to n minus 1, i.e. everything that you've computed up till that point, you generate from some distributions where the parameters of that distribution and the type of that distribution may be functions of the random choices made to that point. Okay? What the heck does this all mean? Okay, so how do we tie together the math and the language? Okay? So how do we read observed statements? So here's some math, and here's an observed statement in the language. Okay? So first thing, the type of the random variable, or the type of the distribution, is Tn, is denoted here. It's first element in this expression. Okay? Note that this can actually be a function of the interpreter state as well. Sometimes you can pick the type according to the state of the memory of the interpreter. The observed value shows up here on the right-hand side. So this is some normal variate that takes value 18. And the parameters are computed from the memory state of the interpreter at that point. Okay? All right? So generative model part 1 is some function that takes two parameters, the parameter of interest 1 and the parameter of interest 2, okay? And that's the parameter vector for this observed statement, okay? So that's the math connection there. What X is a little bit more complicated, okay? It bears explanation in order to sort of see what's going on. And this example tries to get you a little bit towards the complexities that we run into in inference in complete probabilistic programming languages. So what is x1? Okay, so what we're going to do is we're going to execute the program here on the bottom. Okay, line by line. Okay, and we're going to sort of say what x is. Okay, so there's going to be a couple of phases here. So the first thing we're going to do is we're going to execute this first line of the program, which gives us a value for the parameter of interest number 1. We're going to draw from a beta 7-4 distribution. Let's say it takes value 0.4. Okay? Now we can go down to the next line of the program, and we're going to execute this line of the program. The randomness is actually Poisson 8, so x12 is going to be a draw from a Poisson distribution with parameter 8. Okay? So we're going to execute that, and maybe that takes a value 6. Okay? Now this is a little bit confusing. So the next two lines of the program don't actually do anything. They define functions. So the next thing that we execute is actually the observe statement, where we run the procedure generative model part 1 with parameters Poisson 1, Poisson 1, parameter of interest 1, parameter of interest 2. Okay? Running that procedure with the arguments, the first elementary random procedure we encounter is this flip variable, which takes the first argument of the procedure, which happens to be the parameter of interest, which happens to have value 0.4. Okay? So we flip a coin, all right? And depending on its outcome, here we say it takes a value true, then we branch and go down different execution paths. Okay? So now, okay, all right, so that's what's going on here. Okay? So we have to, so having observed that x13 is true, we're in this path, so we draw a Poisson random variate, add 7 to it, and that gives us the ability to execute the next line of code, which is the observe. Okay, so now we have observed normal. We've actually got a return value for this. We know the standard deviation is 1, and we have an observed quantity, and now we can weight that particular execution path. Okay? And we can do the same thing for x12, i.e. the interpreter memory state, after we go through the next step. So we run the next line of the program, so on and so forth. We generate some random variable, and we predict an output. Okay? So we have a sequence of random draws. That is the out and the execution path. Given that the outputs from all of those elementary random procedures is deterministic, that's an execution trace. And what we want to do is explore the space of execution traces that could have given rise to the data or would give rise to the data with high probability. Okay. Prior art is basically single-site Metropolis Hastings, also what I call random database, where what you do is you look into one of these trace objects and pick one of the random variables that you've one of the draws that you've done. Say, for instance, we go in and we pick the draw at this address. Okay, so I haven't told you what an address is, but imagine that we can go in and pick x1 to 3, and we want to propose a change to x1 to 3. Okay, so what we're going to do is we're going to sample a new value for it, try it out. Okay. Now you see what happens here. Things get a little bit complicated, right? So let's say that we sample it and we arrive at the value false here. Okay. That means that we now go down a different execution path, which invalidates part of the execution path and removes all of these samples from our concatenated list of elementary random procedures, or whatever. Okay. And in fact, in the worst case, it can invalidate everything, okay? Which means that you have to run the program again until the very end. Now you have 2 execution traces and the associated log probability with both traces, and then you can do a Metropolis Hastings comparison, or compute a ratio and decide whether or not to accept a new trace or not. So you can walk through the space of traces by doing this kind of thing. The notation that I've put out there should scream to you that this looks like a state space model, right? And in fact, to a statistician, it is a state space model. So what we can do is, instead of doing the single site Metropolis Hastings thing, we can, for instance, envision doing sequential Monte Carlo for probabilistic programming inference, which is an interesting algorithm in and of itself. So sequential Monte Carlo approximates the target density, i.e. the conditional distribution of traces given the observed data, by a weighted set of particles. Well, what are the particles here? A particle, or a sample here, is a trace. It's a sequence of interpreter memory states. Okay? Okay, that's great. So since the model, the way I've notated it, looks and is, in fact, in some sense, a state space model. So we have a state space model like decomposition, where the distribution of interest factorizes like this. You have the next observation, the state space model, the evolution of the program towards the next observation, and whatever our distribution is over the current interpreter state given n-1 observations. Oh, I cannot see that at all. n-1 observations. Then this basically says straight up, let's do sequential importance resampling. Let's choose some proposal distribution Q. Let's make that proposal distribution as simple as possible. We're just going to run the program forward until the next observed directive. Great. And then we're going to weight the particle according to the ratio between the proposal distribution and the distribution of interest. And we repeat this recursively, and we have a sequential importance resampler for doing probabilistic programming inference. Now, this is probably not going to work unless you have a huge number of particles, because the dimension of the state vector grows, right? Okay, so this is really big. This is a huge, huge problem. But what you can do instead, so sequential Monte Carlo hard, but particle MCMC will actually work in this setting, or will do better than prior art. We'll put it that way. It's applicable. So particle MCMC is a new Metropolis Hastings approach to doing inference in general Metropolis Hastings style inference, where you use sequential Monte Carlo as an inner loop. Okay. So in particular, I'll talk today about particle Gibbs, where basically it's a Metropolis Hastings algorithm with acceptance probability 1, i.e. it's a Gibbs sampler, where you run a special sequential Monte Carlo algorithm as its inner loop that uses a retained particle, or a retained path, in a kind of a special way. It's a non-local proposal, and it can change many, many variables at once. Okay? So I have very, very little time, but this is really the heart. I hate to put this up there, but it really is the heart of the contribution, so it's worth going through just a little bit. So particle Gibbs, probabilistic programming interpretation, it says take L interpreters, or L particles, run them for some number of sweeps. The first thing you do is you initialize by running sequential Monte Carlo. You get an estimate over the traces that the program could have taken to generate the data. Then for s going basically to infinity, what we want to do is initialize L-1 interpreters, but keep around a special interpreter from the initial pass. Okay? Then for d ordered lines in the program, fork the interpreter state, actually just copy the memory state, and then depending on what kind of directive you encounter, if it's an assume, you just interpret that statement in that new interpreter in L-1 interpreters. If it's a predict, you just execute that and print out whatever results you have. And if it's an observe, you execute in that new interpreter state and then use the weights to reweight and resample the set of interpreters. Okay? So the diagram there on the left of the slide basically shows L interpreters running forward, them being sampled, killed, so on and so forth, in a sequential Monte Carlo kind of way. The red one, though, is a retained particle that's always reinserted into the set of interpreter memory states. Okay, Anglican is the language that is the research programming language that we've used to test out the particle MCMC. The results is that particle MCMC is applicable to any Turing-complete probabilistic programming language. It supports accurate inference in programs that make use of complex control flow, branching, stochastic recursion, and deals with Bayesian nonparametrics nicely. The theory of particle MCMC, particularly particle Gibbs, suggests that it has very, very nice theoretical convergence properties. Okay, so there's a nice paper here that talks about the convergence properties of particle Gibbs. If you're not familiar with it, you should check it out. Probabilistic programming basically breaks all of the assumptions that are made in these kinds of papers. So the work here is basically establishes experimental evidence that you can get vastly improved, very, very much improved performance over a very, very wide variety of problems. Okay. Little time. So here's the hidden Markov model written in a probabilistic programming language in Anglican. It's a three-state hidden Markov model. It's here only to demonstrate the specific action of PMCMC, which you see here. For instance, what we're going to do is run this program. So what we do is, that's the generative model. We observe some data. We predict the latent states. Okay, the generative model is just a program. It's a three-state HMM. We can go through it in detail at the poster if you'd like. But what we'd like to do is look at how the posterior marginal estimates of the state occupancy distributions converge as you run the probabilistic program and emit samples of the state occupancy. So these are the states that the HMM can be in at particular time steps. And as we run, you'll see that the single site stuff, not terribly surprisingly, modifies a single state at a time and does not mix as quickly per sweep as particle MCMC does. Okay, that's not terribly surprising, but what is a little bit more that is the specific action of PMCMC. It should outperform Metropolis Hastings, and certainly will in the case of an HMM. However, that it's applicable across a wide variety of models and is applicable to all Turing-complete probabilistic programming systems is quite useful. And in fact, the really interesting thing is that particle MCMC outperforms this random DB approach in terms of actual computation performed. Okay, so here we look at the Kale divergence between the posterior marginal distribution of state occupancy, and we count the number of function applications performed. Okay, so in terms of actual compute, actual energy, the estimate of a particle MCMC-based probabilistic programming system, rather than in comparison to a random DB probabilistic programming system, converges more rapidly for the same amount of computation. And we see this for a wide variety of models. So here's like process mixture models, Bayesian nonparametric models, the same story. Whether it's the number of simulations, the amount of wall clock time, the number of applies, doesn't matter. Better convergence characteristics. Programs with complex control flow, same story. So to conclude, forward inference methods for probabilistic programming are actually quite easy to implement. They're very easy to understand. Don't have time to talk about it, but they actually require a very, very simple machine abstraction layer. They really only require a POSIX abstraction. They give you automatic parallel scalability. None of the results plots show any of that. All of the particle filter and PMCMC results are actually single-threaded implementations. So as soon as you get automatic parallel, as soon as you use the automatic parallel scalability, things look really, really good. And the techniques, in particular particle MCMC, are useful in all of the expressive probabilistic programming systems. So thanks to the guys, and I think that's it.